Okay, we have a video here on binomial probability distributions, and this leads on from our work on Bernoulli trials. And Bernoulli trials is based on a single trial. What if we have a sequence of Bernoulli trials and we're interested in determining the probability of a particular number of successes? So if we have a number of trials, so that's what we're about here. And you can see we've got some learning goals over the next couple of videos. We want to understand. We already understand the concept of Bernoulli trials, but let's lead now into binomial random variables. And as I mentioned before, we're talking about a certain number of successes in n independent Bernoulli trials, and p's constant again, like we saw in previous videos. We want to understand that Bernoulli is a distribution, and it's a special case of the binomial distribution, okay, which is thinking sort of in the other direction. So the work on Bernoulli that we've already done is a special case of the binomial distribution, which we're learning in this video, okay, and the Bernoulli is for one trial, n equals 1. And the binomial distribution actually arises from a certain number of Bernoulli trials, as I just said. We're going to start looking at examples of where we can consider things as a binomial distribution situation. We're going to look at, we've already done some of this with the Bernoulli. We're going to look at n, p, and q. Remember, q is the complement of p, and we're going to deal with binomial with and without technology. Need to be across both, and we're going to use the values of the parameters for a binomial situation to determine the probabilities. That's the point, okay, to find probabilities. Okay, so you need to have a bit of a background on binomial expansion, which is in other videos, and hopefully you've seen that before. And you might have seen it in various formats, some of it with the NCR effect on the front, or sometimes without it. We're going to lead up to where does this binomial probability formula you see there come from. Okay, so it's actually linked to the binomial theorem expansion above it. Please bear in mind, in regards to the binomial probability formula, we see different symbols being used, but they can just mean the same thing. For example, we could have parameter x instead of r, and it would still be essentially the same formula. You might see an x there. In the NCR would be actually be NCX to be technically right. So we got p to the x and the complement 1 minus p. We know that's q, don't we? 1 minus p to the n minus x. It's just the same thing with the r's and the x's swapped around, because you've seen in the past we often use the parameter x when we're looking at a certain number of successes for particular cases. Okay, so let's link to what we might have learned already in maybe junior probability, things like year 9 and year 10 level probability. If we've got a situation here where let x be the number of threes, okay, so if we're looking at the number of threes on, say, a fair die, okay, so x is a success, a number of successes, and this is, in this particular case, it's the number of times a 3 on a die, okay, shows up. Alright, so we're looking for on the die, you know how a die might be a numeral or it might have the dots. We're looking for a 3. That's our definition of success. And we're actually doing also 3 throws of the die. Don't get those 2 3s mixed up. Okay, so n equals 3. Now what you might have done in junior, because it's not an enormous problem, we can put it in a table. And so you can see here where, by the way, the t there means getting a 3. That's a success, and n is not. Okay, so what you can see is all the possible outcomes. So we could get 3 threes. It's possible, so therefore x would be 3. And we know that on each throw of the die, because it's independent, it's 1/6 times 1/6 times 1/6. So this and this and this, using the multiplication principle, and we get 1/6 cubed. And then we've got the case of getting 2. Alright, so these are where we get 2 threes. There's 3 ways of that happening. Okay, could be on the first and the second, could be on the first and third, and then could be on the last 2. Likewise with 1 3 and 2 non-3s, and then no 3s at all. And you can see the corresponding probabilities there. They should be fairly obvious. Now, that's not too bad. It takes a bit of work, but it's pretty easy going. Okay, if we crunch all that and look at these, for example, 5 6 to the power 3 is 125 on 216. So if we evaluate all those, we get all the probabilities associated with the sample space, and the sum of that equals 1. All right, because all probabilities from all elements of the sample space, you add their probabilities together, it becomes 1. That's the whole distribution. All right, that's the result of the entire distribution there. What if the distribution was bigger than n equals 3? Well, it takes more work. If we have, let's say, 5 multiple choice questions on a student's exam, and this naughty student didn't study, and they have to guess all 5 questions, they've got absolutely no idea. Each question has 5 different choices, and the student plans to randomly guess the answer for every single one. So let's say C is guessed correctly and I is guessed incorrectly, and there are a bunch of different ways that could happen. We could have no correct answers, okay, and then we could have 1 correct answer, 2 correct answers, 3 correct answers, 4 and 5. And there's various different ways this can all happen. Now you can see down the side here we've got different working for this. You could use the multiplication principle, but it starts to get pretty big, and you can see the use of a formula here too. So what does all this mean? The bigger the distribution, the more elements in the distribution, or the more number of elements or number of trials, the more work it is using this whole method. So let's see if there's a better way. Can we see if our binomial theorem or our binomial expansion helps? Now, basically, if we've got something to n equals 3, we've got something raised to the power 3, and we could say x cubed plus 3x squared y plus 3x y squared plus y cubed, or in terms of p and q, same thing. Now, p plus q equals 1 for a Bernoulli trial, so that would actually be 1 cubed. So this would actually equal 1 in terms of probabilities. So that would be p cubed, p squared, q plus p q squared plus q cubed. So where do all these come from, and how do we find that out? And how do we apply it to probability? Perhaps you've examined some of the theory behind the binomial distribution, but even if you haven't, we can explain now that if we have each term, this term here I'm highlighting is one of them, we follow this pattern. So the first one would be nc0 times x to the n. Alright, next one is nc1 times x to the n minus 1 times y. And then we just keep moving through. So we would have nc2, and then x would be n minus 2, and y would be to the power 1. So for each term, we have this here happening. So for the rth term with n total trials, or n total elements, we have ncr x to the n minus r times y to the r, where x is the first element and y is the second. In distribution, the two elements are p and q, or they might be called p and 1 minus p. Okay. The NC part bit at the front is the number of combinations. It's the number of ways each of these outcomes can happen. And if we look back at the simple example here, not all of these outcomes can happen in the same number of ways. For example, getting 3 3s can only happen in one way. Getting 2 3s can happen in 3 ways. getting 1 3 can happen in 3 ways, and getting no 3s can only happen in 1 way. So that allows us to correctly ascertain how many different ways this can happen. Okay, and that affects the calculation for the probability. You can see that these have 3s on them. Note the correspondence in this example. We have 1 3 3 1, and in these distributions I did here, in both cases we have 1 3 3 1. That's no accident. So the binomial distribution allows us to work out the probabilities in the entire distribution, but more usefully, for a particular one, it allows us to work out the probability of that particular case for a particular number of successes. And that's what we're trying to do here. So in general, make sure you know this and you know how to use it. And just note that it can be with some slightly different notations. So that's important there. Let's look at one example. And also we'll look at the example we rushed through before, the one with the correct and incorrect number of guessed answers. You can see that in each case we've looked at that same formula. So what's the probability in that situation of that student who didn't study of getting 5 incorrect answers? You're probably feeling by intuition that it's kind of got a reasonably good chance. So, using the appropriate element of the binomial expansion, in the first case, remember defining success as guessing an answer correctly. That would mean the parameter, it would be x equals 0. So we have 5 is the total number of trials, C0. The probability of getting a success on any particular Bernoulli trial, well, there's 1 out of 5. There's 5 choices in each of them, you might remember. Okay, and it's to the power 0 because r is 0. Then the q, the complement of that, is 4/5, and then we have 5 take 0, which is 5. And that comes out as 0.3277, so it's a pretty good chance. It's almost 1 in 3 chance, okay, of getting none right at all if you had to guess. That's pretty dismal. Okay, now getting 1 right out of 5, it's actually 1, 2, 3, 4, 5 ways of that happening, but we simply just use the NCR to work that out, and we plug in the corresponding values, and you can see that we get the probabilities, so on, and we continue down here, and you can notice that these numbers change according to the rule there. Alright, so R is, in this case, is the number of correct answers, and that will affect all of the R's in the formula appropriately. P stays constant, as you know, with Bernoulli trials. You can pause the video and have a look at how it's worked with all the others, but that should make sense. So the chances in this scenario of guessing 5 out of 5 purely by guessing with 5 options in a multiple choice exam is a very tiny order of probability. Very tiny indeed. Even getting 4 is 0.6 of 1%. Even getting 3 is only a 5% chance. So having to guess in a multiple choice exam is perhaps not a good policy, especially if there's 5 options. So the moral of that story is study and make sure you know your work. Okay, and there's the full distribution there. And if we use the binomial expansion, that would be all the values, and of course they add together to be 1 because that covers the entire sample space. Finish off now. So here's an example. Find the probability of obtaining exactly 3 heads. So not at least 3, not 3 or more, or less than 3, or anything else. It's exactly 3 only. So your 3 heads when a fair coin is tossed 7 times. So we've got n equals 7 here. Okay, so define a success, remember, as we do with Bernoulli trials, even though this is a sequence of them, getting the head on the coin is considered to be the success. The probability of each is constant and it stays at 0.5, okay, because it's a fair coin. So x is the parameter involved, it's the number of heads obtained, because that's the success we're looking for. In this case, n equals 7, p equals 5, they're our parameters. Alright, So we use our formula, the NCR formula, whether using NCX or NCR. Okay, and we have n minus r there. Okay, and you can see that those are subbed in appropriately. Interestingly enough, there's 35 different ways that can happen. There's 35 different combinations. That would mean we've got 3 heads and 4 tails, okay, because of all the different orders involved.